In today's class, we are going to talk about some existence results. So essentially, let us recall a little bit, some quite small recall. Okay, given a problem, let's just solve the homogeneous problem, yeah, and then we will dive into the non-homogeneous, or I mean, maybe we talk about this. Okay, so let's say you are given this problem: Laplacian of u equals to f in omega, and u restricted it to the boundary is 0. Yeah, this is called, if you remember, this is called the Dirichlet problem. The Dirichlet problem. Okay, I mean, of course, it's called a Poisson equation. See, this equation is called Poisson equation. This equation, yeah. So let me give it like this. I mean, maybe Laplacian of u equals to f. This equation, only this equation is called the Poisson equation, right? Poisson equation. But I mean, if you take this equation, yeah. So, but let's say this equation, Laplacian of u equals to f in omega, and you are putting this initial condition. Let's say u equals to g, yeah, or 0. It's not a big problem. But essentially, the data is given only on u. Yeah, if that sort of thing is there, this problem will be called a Dirichlet problem. Okay, sorry, it's Dirichlet. Dirichlet problem. Okay, it is named after the mathematician Dirichlet. Now, and let's say you can also have this kind of problem, yeah. And the method which I'm showing, you can actually modify the method to deal with this sort of problem also. Del u, del eta, yeah. So this is outward normal on the boundary, g on del omega. Okay, so basically delta is the outward normal at every point on the boundary. So del u del eta, that is equal to g on the boundary. So this is called a Dirichlet problem. If the data is given on the partial derivative and not on u, then this problem is called a Neumann problem. Okay, it's called a Neumann problem. So today what we are going to do is basically look at the Dirichlet problem. So let's say let's call it a g. Yeah, so minus let's call it a, it does not matter. I mean, you can take minus and not minus, but let's just call it a minus. Huh? See, the thing is this f is arbitrary, right? So, I mean, if you are not convinced, you just change f to minus f. So, Laplacian equals to exactly, some minus f, which is g, which is h. Yeah. So, it does not matter. It's just a convention which we use, minus Laplacian of u equals to f. Okay, now the point is this: we want to solve this equation, right? So you remember, given a ODE, what are we trying to do? So our quest is this: our quest is to address the well-posedness. Okay, let's say the axial 1, well-posedness of 1, right? Well-posedness of 1, yes. And in that respect, what did we saw? We saw that, I mean, you can use maximum principle to show that the stability is there, right? Yeah. So for small change in the initial data, the problem, the solution changes a little bit. Yeah. So the stability. So this is the recall. The stability question, or I mean, this change under the perturbation. Stability can be addressed. Okay, stability can be addressed using maximal principle. Yeah, but please remember this thing: maximum principle. Most of the maximum principles which we did are valid only for bounded domains. Yeah, I mean, some are for unbounded domains. You can prove those. Yeah, but the maximum principles which we proved are only for bounded domains. Yeah, and so stability can be addressed using maximum principles, and there is another thing called uniqueness, right? Uniqueness. So uniqueness, we have seen that you can use uniqueness is there. So you can use energy methods for uniqueness, energy methods, and what is there? Moreover, you can also use maximum principles, right? Maximum principles. So those things are taken care of. Now, the only thing which is remaining and the most important thing is how do I find a solution for this problem? Yeah. Okay. So let me clarify this thing more. So essentially, What is the question now? The question is existence. Existence of minus Laplacian O equals to F in omega, and U restricted to the boundary is G, right? Now, for our case now, in this case, we actually assume that F can be, F and G are smooth, yeah? So don't worry about what is the regularity of F and G, they are smooth. And what about omega? Omega, so where omega, yes, omega is of course is a subset of Rn, yeah, there is nothing to say. So omega is open, okay, bounded, very important here. So this what I'm going to do now, that for that omega has to be open, bounded, and the boundary of omega, del omega, is in C1. Yes? Or I mean, you can also say omega is smooth. So basically, the domain is smooth, which means that the boundary is C1. Yes? Okay. So, or I mean, we also say that the smooth domain. Okay. This is basically saying that this is a smooth domain. Okay. Right. Now, what I want to do, I want to find an existence of this problem. Before I go on doing whatever I'm trying to do right now, let me make some small remarks. So please keep this thing in mind, remark. See, what I'm going to do is I'm going to construct something called a Green's function, yeah, for a particular domain, for a given domain, there exists a Green's function, okay, Green's function, okay, which can be utilized to find solution of star. Is this clear? We'll show that. Yeah, we will do all that. Don't worry about it. So we'll write down a formula of what UX will look like, right? The explicit formula of UX based on F and G. Okay. So if you are given a domain for that particular, please remember this thing, for that particular domain, you can find a Green's function. And this is a theorem, right? That you, for a nice enough domain, you can actually show that there exists a Green's function. Yeah. So that is there. I mean, we will do that. We will show that. So, but in reality, so basically you may say that, yeah, then for any domain, I can just find a Green's function and write down the explicit for a formula for this thing, right? Any solution of that will look like this. You do understand what I'm saying? See, Green's function, once you, for a given domain, yeah, I mean, take any domain. Let's just say that the domain is a ball, yeah, with center at origin and radius 1. So for that given domain, let's say you found out a Green's function, and with the help of that, you have just found out what the solution UX looks like. Yeah, okay, fine. Now, and since you know that the solution is unique, you can say that is the solution which you are looking for. But the problem is this, see, for that particular domain, yeah, for the unit ball, how do you find the Green's function? That's the question. But in reality, what happens is, if omega does not have nice geometric properties, okay, geometric properties, this is very important, okay, geometric properties. So in some places you will see that they start constructing Green's function out of nowhere. Yeah, most of the places where you can see that, I mean, does not have any motivation of how those Green's functions are coming. Yeah, and most of the times they are like, it's like it's not based on any logic. Yeah, you just, I mean, try your hand on something and get the Green's function. Yeah, and most of the times you won't find. That's the point. See, Green's function exists for a C1 function. That's for sure. It exists. Yeah, but finding an explicit Green's function is almost always impossible. You understand? Except for a few nice domains. Yeah, if omega does not have a nice geometric property, and I can't specify what sort of geometric properties I'm talking about right now, but we'll have some idea about what this means. Yeah, then finding an explicit Green's function, Green's function is almost always impossible. Okay. Now, you may by some hook and crook for some domains you can get it, yeah. But generally speaking, it won't be easy. I mean, not easy. I mean, it's kind of an impossible task to do. Okay. So, with that in mind, please, I mean, let's start with finding at least for some problems we can find, right? And let's do that. Yeah. So first of all, let us show that there is a Green's function, yeah, which I mean solves our problem. Okay. Let's just call that problem star. Yeah. So this is star, right? Okay. We want to solve this problem. We want to find a ux. How does ux look like? Okay. So proof. Yeah. So basically the derivation. I'm doing the derivation of Green's function. Green's function, right? Derivations of Green's function. Now, so let's say I'm starting out with a u which is C2 omega bar. Okay, there is nothing special about this u. I'm not saying that this is Laplacian u equals to 0 and all that. Nothing. Yeah, it's just an arbitrary function. Yeah, is an arbitrary function. So you start with any arbitrary function which looks like this. Clear? Okay. Once you do this, then what I'm going to do is I'm going to employ a similar tactic which we did in the last class. Yeah, for the convolution thing which we did last class, that sort of thing. So basically, we'll fix a u, we'll fix a x in omega, okay, and epsilon greater than 0 such that bx epsilon is contained in omega. Okay, and we apply integration by parts on, let's say we call it omega epsilon, yeah, which is omega minus bx epsilon. Okay, why we are doing it to be clear right now. So basically what we are doing is this. Let's say that's your omega. Okay, this is your omega and that's a point x. Okay, take a small neighborhood of x. Let's say this is x. Yeah, that's epsilon neighborhood. Yeah, I'm just throwing this part out and this is your omega epsilon, right? This is your omega epsilon. Omega epsilon. Yeah. So I want to work on omega epsilon right now. What I am going to do here is this. See, I am going to use integration by parts, but for in this domain, in this domain, for which functions? U of y. Okay, u is a function of y. Okay, see this x is fixed. I am fixing an x in omega. Yeah, and for that I am using integration by parts on this u, which is a function of y right now, and the fundamental solution, if you remember, phi of y minus x. Okay, and now I am sure you have some idea of why we are taking this deleted neighborhood. Yeah, because y, when y is equals to x, phi blows up, right? So we don't want want that thing to happen. So in this omega epsilon, you see y, if I'm starting out with a y in omega epsilon, that can never be, I mean y can never be equals to x. So phi is well defined here, right? And of course u is always well defined everywhere in the domain, so it's not a problem. Yeah. So I can use the integration by parts, and once you use that, what happens? Let's say omega epsilon u of y Laplacian of, yes, phi of y minus x minus phi of y minus x, yeah, Laplacian of u of y dy. Clear? So this is equals to integral over the boundary of omega epsilon, yeah, u of y and del phi del gamma of x minus y, okay, and minus maybe I don't know, maybe let me write it like this, okay, and here also let me put it like this, minus phi of x minus y, okay, del u del gamma of y ds y. Okay, so this is just an integration by parts. I just took two parts and put it together. Okay, I mean nothing much, right? So once I have something like this, okay, gamma I didn't specify. Gamma is the unit outward normal on del omega epsilon. Clear? That's your gamma. Okay. Now let's look at see. So there, hence let's call this thing as it's a big expression, right? Let's call this for now. Let's call this an A, and this expression as B. Okay. So what do you have? I have omega epsilon A dy. Yeah. A of y, of course. A of y dy equals to. So this is A of y and this is B of y. Clear? This is A of y and this is B of y, and that is equals to del omega epsilon of B of y ds of y. Okay. So now let's break this part. Yeah, d epsilon y. So this is, see, what is the boundary of epsilon y? Epsilon y is this interior points, right? It consists of the interior points. So the boundary is, of course, the boundary of omega plus the boundary of this ball, right? So it's basically the boundary of ball with center at x epsilon, b of y. Okay, let's call it b tilde, because ball I am writing as b. So let's say this, call it a b tilde. B tilde is this expression, yeah, the big one. So b tilde of y ds of y. Okay, plus the integral over the boundary del omega. If you remember, the boundary is this boundary. The boundary of omega epsilon is this one plus this one, right? Okay, so I'm just breaking it up like that, and b tilde of y ds of y. Clear? Now let us look at this expression. Omega epsilon del b x epsilon phi of y minus x del u del gamma of y ds y. Okay, this expression I want to calculate what happens to this. See, b tilde has two expressions, right? B tilde is this one, right? So I'm just starting out with this one, right? I'm not touching this one. I'm just starting out with this. This is phi times del u del gamma and integral over the boundary. Yeah? Integral over just this one. I have also this part to take care of, but let's just stick with this. Okay, for that, what do you have? See, del u del gamma. U is a C2 omega bar function, right? Yeah, U is a C2 omega bar function. So this is continuously C. U is a C2 omega bar function, and this ball is contained in omega. Yeah, so U is continuously differentiable. Yeah, so on the boundary of the ball, yeah, there is a maximum which U is attaining, and that maximum I can just take it outside. So basically, this is less than equals to the maximum of del u del gamma, okay, on b x epsilon, del b x epsilon. Yes, that I can just push it outside, and once I do that, I am left out with x epsilon phi of y minus x ds y. Clear? That is what I have left out with. Now see what phi. So essentially, if I'm taking y from this, yeah, see, I'm doing this integration, yes, such that y is on the boundary of this. Where does y lie? Y lies on the boundary of the ball centered at x and radius epsilon, and I want to integrate phi of y minus x here. So as you guys know, phi of basically y minus x is some function r of mod y minus x, right? Yeah, because phi is a radial function. Clear? So if it is a radial function, what happens is basically a constant on the ball, right? I mean, y minus x, this is constant there. So essentially, you can just take the maximum of this phi outside. Yeah. Okay. So this is, if you take that particular thing. Yeah. So essentially, what I'm trying to say is phi. If you are taking y from the boundary, y minus x is something epsilon. Yeah, y minus x is epsilon. So essentially, what is happening? You are basically integrating 1 by, or I mean, if you want, you can just, you see, if y is never equals to x, I mean, you can also think of, I mean, see, there are many ways of doing this thing. Yeah, you can also think of it like this: x is not equals to y. Okay, because x is in the center and y I am taking from on the ball, on the boundary of the ball. So x is never equals to y. There is always an epsilon distance between this. Okay. So this is always defined, well defined. Yeah, this is and it's a continuous function. So you can also take the maximum outside. So basically, maximum of this and maximum of this. Let's say that's your C. Let's say this is your C, and I'm again taking maximum of phi. Let's say, yeah, I can take that outside also. So again, this is on the same thing. Yeah, and you have the integral of del B x epsilon dsy. Yeah. So if you take the integral, that's basically the surface area, right? So that will look like epsilon power n minus 1. Yes, surface area, that's epsilon power n minus 1. Of course, some constant is there, and that is getting absorbed here. Yeah, I'm not writing all that. So this goes to 0. Yeah, as epsilon goes to 0. That's quite evident. Is it clear? Okay. Now, what we have is this. So also integral over del B x epsilon, okay, u of y, the other part, this is there, the other part is u of y del gamma of phi, right? Okay, so u of y del phi del gamma of x minus, y minus x ds of y. Clear? Okay. Now, what exactly is this thing? If you remember from the last class, if you remember, we did this kind of exactly this sort of calculation. Yes. So what did we get? We get something like this. Yeah. I'm not doing this part again. Sy, and which goes to u of x. Yeah. If you remember, while proving that the convolution with phi and s, that solves the Poisson equation. Yes, in Rn. Yes. When doing the last calculation, this is the last part of that calculation. Yeah, if you remember, please go through that if you don't remember that. Yeah, so this is also true as a student studio, of course. Yeah, as a student studio, we did the exact same calculation. I'm just using that. Yes, I'm not doing anything special here. Okay, so once you have something like this, then therefore the formula which you have is this. You see, this is u of x. Yeah? If you just put it together, yeah, let's just put it together. This is u of x, this is going to 0. So essentially, you see here, this term will be there. Yes, this term will be there. From here, you are only getting u of x. Clear? Because one is this part, b tilde has two parts. One is going to, this is going to 0, and this is going to u of x. Yeah. So essentially, I can write it as u of x is equals to integral over the boundary phi of y minus x del u by del gamma of y minus u of y del phi by del gamma of y minus x. Yes, and dsy, okay, minus integral over omega phi of y minus x, okay, Laplacian of u y dy. Okay, so this is what we are getting, right? If you see, where is it? Yes, we are getting this. Why? Because what happens to this term? This particular term is 0, right? This particular term is 0. Y is never equals to x. So Laplacian of phi, this is a fundamental solution. This is always 0. So essentially that is gone. I am always left out with the minus integral over omega epsilon phi of y minus x Laplacian of u of y dy. So omega epsilon, as epsilon tends to 0, becomes omega. So integral over omega, only this particular thing. Yeah. So that is what I wrote. Where is it? You see, that is what I wrote. Yes. Okay. So of course, and this, so let's call that as 2. Okay, so and 2 is valid for all u in C2 omega bar and x in omega. Yeah, you can do it for any x in omega. It does not matter, because for any x in omega you can always find a ball doing that, right? Because omega is open. Okay, so here you see what is happening. If you know, let's just assume that if you know what Laplacian of u is in omega, so let's say that's your f. Yeah, phi is already known to you. Phi you already know, because phi is a fundamental solution, right? It does not changes. So essentially, you can just calculate what is integral of omega, integral of this particular thing over omega. Once you know what Laplacian of u is, yeah, and that is given to you. So basically, it is given to us that Laplacian u equals to f and u equals to 0, u equals to g equals to boundary, right? If you look at the star, see, if you look at star, where is star? Laplacian u equals to f is given to you. So just replace that there, and u restricted the boundary is g. It is given to you. So let's see. This function, this holds for any u in C2, right? Yeah. So what I'm going to do is I'm just going to write down here. If I put it there, you see this Laplacian of u, yeah, this is f minus Laplacian u equals to f. So replace it by f. This already we know, so we can calculate this. Let's look here. C we already, okay, let's look here. U on the boundary, we know if this is G, and del phi del gamma on the boundary we can calculate, because we know what phi is, we can just calculate what del phi del gamma is. Okay, what about this one? Phi we know, but del u del gamma, this is a problem, right? Del u del gamma, see, we know what u does on the boundary, we don't know what del u del gamma does on the boundary. Okay, so we have to somehow eliminate this particular expression, and then we can go through what we are trying to do. So this is where we are just trying to construct a Green's function. So to do that, what we are going to do is we are going to introduce a corrector function. Okay, a corrector function, so that is given by phi of x, which is phi x of y, phi of x, which is phi x of y, and it solves the boundary value problem. Okay, it solves the boundary value problem. How does it solve? It does this. Laplacian of phi x equals to 0 in omega. Okay, phi of x is equals to phi of y minus x on the boundary. Okay, so what we are going to do is for a fixed x. So this is for a fixed x in omega. What we are going to do is this. See, we are going to fix a x in omega, and for that we are going to introduce a corrector function, okay, which is phi x given by phi x of y. Okay, so for every, please understand this, what we are trying to do here. We want to eliminate this del u del gamma term. Yeah, to do that, we are fixing a x in omega. Yeah, so once we fix that x, we are introducing a new function based on that fixed x, which is phi x of y, and such that Laplacian of phi x is 0 in omega, and phi x is the fundamental solution evaluated at y minus x on the boundary. Is this clear? Now let's apply the integration by parts again. Once we apply integration by parts, we of course get this here. Let me write it down. It is phi x of y Laplacian of uy dy equals to integral over the boundary del omega u of y d phi del phi x by del gamma of y minus phi x of y del u del gamma of y ds y. Okay, so basically I'm just using the integration by parts to write this thing. Okay, I hope you understand where this is coming from. Yeah, so this is just whatever we did earlier. This is the same integration by parts. So this is just this formula. Yeah, this formula. Laplacian of phi x is 0, so I'm not writing that part, and except that everything is same. Okay, I'm just writing that particular formula, you see. Okay, so of course not for that function. I'm using that formula, but for this function phi of x and u. Okay, once I do this thing, so let's say this over del omega. Yeah, this will look like u of y del phi x del gamma of y minus phi x at y is capital Y minus x, okay, del u by del gamma y ds y. Clear? You have this. Now you see what is our point? Our point was to eliminate this particular term del u del gamma at the point y on the boundary, and this is the term, right? Phi y minus s del u del gamma on the boundary. Yeah. So if I add this term and this term, then they have to get cancelled out. Yeah. I want to eliminate that only. So adding this thing. So maybe yeah. So what we are going to do is now we want to add those two terms, and to do that, I mean, we want to make it a little simple. That's all. Yeah. Now we define. So now we define. You understand what I'm saying? See, if I add those two terms, this term is gone, right? If I add this particular term and this term, I want to eliminate this term. So basically, if I add this expression and this expression together, that term is gone. Okay, and I want to do that, and I want to write it in a more compact form. Yeah, and that is why we introduce a new function. So we define Green's function. Yeah, this is what we call the Green's function. Green's function. Okay, for the domain. You see, Green's function is not for anything. It is only for the domain omega. Okay, is g of xy. We always write Green's function as g of xy. So this is equals to, this is by definition, the fundamental solution at y minus x. Please remember, the fundamental solution is defined in whole of Rn. Yes, and that is why I can just write it like this, times Cx of y. Okay. So this is what x and y is in omega, and x of course not equals to y, because otherwise this is not defined, right? So this is a Green's function which is defined. Now once you define this thing, then adding, let's call it, so that's your 2, right? This is your 2, yeah, and let's call it 3. Okay, so adding 2 and 3, we get, what do we get? We get u of x is equals to minus integral over the boundary u of y del g. I am just writing it down. Yeah, please calculate this thing. It's not very difficult to do. I mean, it's very easy to do. Please check that part. That's all. dsy, okay, minus integral over omega g of xy Laplacian of u of y dx. Okay, so this is for x is omega. Okay, that is u of x. Of course, here where del g del gamma of x comma y, this is given by gradient of g at the point xy. Now when I am writing gradient of g, I mean it is with respect to y. Okay, so essentially g with respect to y, that's all. Okay, times gamma y. You understand? This is g with respect to y. Okay, right. So dot gamma y, and of course the gamma is the unit outward normal. I'm not writing all that. Gamma. Okay, let me write unit outward normal, whatever the domain is. Yeah. So in this course, I mean, please just keep this in mind. Whenever we write this del g del gamma kind of thing, you will always understand. It's always understood that this is the unit outward normal. Okay, unless otherwise written. Okay, so that's the thing. Now you see, so basically what I'm trying to say is, once you find this g, yeah, you can just replace this g here, and you can, you find what u of x is, and we're done, right? Yeah. So let's write down the representation formula. This is called the Green's representation formula. Okay, representation formula. Okay, so what it says is, if u is in C2 omega bar, okay, solve star, then u of x, okay, is written as minus integral over omega over the boundary g of y del g del gamma of xy dsy plus integral over omega f of y g of xy dy. Clear? Okay. I just wrote this in. See, Laplacian of u is f, right? Minus Laplacian of u is f. So that is why this is plus f times g. Yes. Minus integral over the boundary u of y times this. So this is remaining unchanged, del g del gamma. I am just writing, and u on the boundary is g. So I am just writing it like this, and that gives you a representation formula for any x is omega. Okay, and essentially what we did is, let me again just recall. We wanted to find the solution of a Green's function, the solution of the Poisson equation, right, with the Dirichlet boundary data. And to do that, what we did is we found out a Green's function. So the main important thing here is to find this indicator function. What is the indicator function? Yeah, to find this, the corrector function. Yeah, corrector function. Once you find the corrector function like this, so the important thing is this. See, if omega is C1, this is easy to find, right? This is always true. It's not a problem. For any u in C2, if omega is a smooth domain, this is always true. Yeah, you don't have to worry about it. The only worry is, once you find a corrector function, you have to find a corrector function for that omega. Yeah. Now, it may look like not a very difficult thing to do, but it actually is the most important thing which you can, this is the difficult part. Yes. So to find the corrector function, here I defined it like this, but in real life situations, if you have to solve the problem explicitly, you have to find the corrector function explicitly. You understand? That is going to be difficult. Yeah. And once you find the corrector function, you just define a Green's function like this. There is nothing special actually. You can't I just defined it just to make it short. That's all. So once you define this thing, you do realize that what happens to g on the boundary, it is going to be 0, right? G on the boundary of the domain is going to be 0. Yeah. And so you just have to find a g which does this, and then you just write down the representation formula in terms of this function g. Okay. So one small thing, so a remark, and this I want you guys to do it yourself. Okay. It's just some calculation, but I hope you can do this. This is called a symmetry. Symmetry of Green's, this is Green's function. Symmetry of Green's function. So what does it say? It says that g of x comma y, yeah, this is equals to g y comma x. Yeah, this holds for all xy in omega such that x is not equals to y. Is this clear? Okay, this is called a symmetry. So essentially it is saying that if you change x to y or y to x, does not matter, it does not change anything. Okay, it remains the same. So you guys have to check it yourself. Please check it yourself. Check it yourself. Okay. So please do that. This is just a property of a Green's function. Okay. So once you do that, you are done. Now, in the next part, what we are going to do is we are going to see how to find a Green's function for a particular domain. Okay. So with this, we are going to end this lecture.